So, we will continue with solving our equation for the steady state. So, you remember this is the equation that we came to, which is if we now write it in terms of liquid. So, this becomes del CL over del T with respect to interface reference frame is equal to dl, which is the diffusivity in the liquid, del 2 by times del 2 CL by del x square plus V del CL over del x. And there were two conditions where there is steady state and when there is transient, when depending on whether this is 0 or not. So, we are assuming that this is 0 for the first case where it is steady state. So, for the steady state, we are not assuming steady state implies that this is equal to 0, and therefore, we are left with this equation, which is this is a very standard equation in differential equation, and there is a very standard solution for this. So, we will write what is the standard solution for this. Standard solution is of the form CL. So, the solution for this will be CL as a function of x. So, CL is equal to alpha times exp, which is exponential beta x plus gamma. So, this is a standard solution for equations of this form, where alpha, beta and gamma are some constant values. We can find out those values by putting in the boundary conditions. We know already some of the boundary conditions. We have seen that CL is equal to C naught at very large distances, which means at x equal to infinity. So, at x equal to infinity, CL is equal to C naught, at x equal to 0, CL is equal to C naught by k. Let us take double differential of this, differentiate this with respect to x, and then double differentiate it with respect to x and put it back into that equation. So, we will be able to get something out of it. Let us see what do we get. So, first differentiating with respect to x, we get beta will come out, beta L times alpha times exp beta x. Gamma is not a function of x, so it when you differentiate it, it becomes 0. Now, when you take second differential del 2 CL by del x square, this becomes beta square alpha exp beta x. So, this is the second differentiation. Now, let us put this back into that equation. So, dl times this plus V times this is equal to 0. So, we will get dl beta square exp beta x plus V beta alpha exp beta x equal to 0. Now, assuming that exp of beta x is not 0, we can cancel that out, and what we will be left with is this. So, we have obtained one constant, value of one constant for this equation. Now, let us try to find the other constants, and for that will, although I am erasing this, but remember what are the boundary conditions, because we will need these boundary conditions to solve to obtain the other constants. So, our CL now becomes alpha we have not yet obtained gamma. So, gamma is still there, alpha is still there, and we have obtained beta. So, we have put that beta into over here. Now, like we said, we will put the boundary conditions, just let me write it in a small note over here, CL equal to C naught at x equal to infinity and CL equal to C naught by k at x equal to 0. So, you put this x equal to 0 and what you get is CL equal to alpha plus gamma, because when you put x equal to 0 this whole thing becomes 1. So, this is alpha plus gamma and this is equal to C naught, sorry this is equal to C naught by k, and therefore, you can say that alpha is equal to C naught by k minus, okay, I have missed one step over here, which is when you put x equal to infinity over here. So, if you put this one, what you will get is C naught equal to gamma. Now, when you put x equal to infinity, this term goes to 0, this term becomes C naught. So, C naught is equal to gamma. In the second one, which is this one, when you put x equal to 0, you get CL equal to alpha plus gamma equal to C naught by k, and therefore, alpha is equal to C naught by k minus gamma. But from here we know that gamma is equal to C naught, therefore, we can say alpha is equal to C naught by k minus C naught. So, now we have obtained alpha, beta, gamma, all the three constant values. Now, we are in a position to write the equation CL in terms of the known parameters, and you would see that it comes out to something like this. So, for the condition of no solid diffusion with limited liquid diffusion and in the steady state, we have obtained the concentration profile of the liquid. So, if you were to look at what we are talking about, let us again draw this plot. We had this C naught and somewhere the solid is forming, and since the solid is it is in the steady state where we said that the crystal is so long that the solid concentration is also equal to C naught. So, this is the concentration of solid over here. Over here we do not know, it is the transient state. So, somewhere over here it has reached steady state, and at this point this is the concentration of liquid. So, this beyond this is the liquid concentration like this, and what is the maximum, what is this concentration of the liquid here, which is our x equal to 0. This is what we said is C naught by k, this is C naught, and at x equal to infinity you can see. So, if I want to draw it in a way, let us draw liquid in blue. So, this is the liquid part, and let us draw the solid in the red part, and here I have left it open because this is the transient state for which we have not yet talked about. So, somewhere it reached a steady state, from where on the solid has a concentration C naught, and at the point where the solidification is taking place, just at that point the liquid concentration is C naught by k to begin with, that is at x equal to 0, and at very far distances it is again C naught. So, we are describing, this equation is describing the concentration profile of this liquid. So, this is what we have obtained yet so far. So, this is the steady state condition. Now, what is the non-steady state condition and what do we obtain over there? Let us look at it. So, non-steady state or transient state. How is it different from the steady state? Simply because del CL over del T is not equal to 0. So, this value is still finite and it exists in the equation. So, this becomes del C, your diffusion equation becomes d del C over del T times dl that is the whole, all the terms are there in this particular equation, we cannot cancel out any of these terms. Now, again if you want to solve this, it is a very difficult condition, because if we were to draw it, then this is how it would look like. There is a C naught, and somewhere over here the liquid the solid that forms, it starts with C naught by K, but beyond that we do not know. Just because I know, I will just draw it like this, it will somewhere like this. So this is up to this, it is a transient condition somewhere here, and at this point let us say there is a liquid, it will have a concentration. So if the concentration of the solid is CS1, this will be corresponding CL1, which you can obtain from the phase diagram, and again the liquid concentration would be something like this. Now you see this whole thing, what will happen to the solid concentration? Solid concentration will slowly reach C naught, and therefore this whole profile, this concentration of liquid at the x equal to 0, all of those will change, and that is why we say it is a transient state. And since what is the concentration of the liquid is not so important, we were looking at liquid concentration because that is the only thing that is changing. Here what we are more interested in is how the solid concentration is changing, and for that people have found solution for very small values of K. So like I said, this problem is not so very tractable, we will not try to solve it, but I will give you solution which has been obtained for certain condition, which is for very small K values. That is when you are talking about slopes which are very large over there. The slopes of the liquidus and solidus are very large, or in fact what we have is the solidus has very large slope and liquidus has very small slope, then you will have very small K values. And for this it has been shown that the concentration is CS So note that we are here talking in terms of concentration of the solid, because the liquid concentration is not constant, it is varying with time. Overall we do not know the liquid concentration, we cannot at least from now, for now on at this point we are not in a position to define the concentration of liquid. But if you know the concentration of solid, of course you know that at this particular interface, because of the equilibrium interface, what should have been the liquid concentration. So although we are not talking in terms of liquid concentration, you can still obtain liquid concentration from over here. On the other hand, here we are talking only about the liquid concentration, because the solid concentration in the steady state is equal to C naught throughout in the steady state, only in the steady state region. So these are the two different conditions, steady state and the transient state, for the condition of no solid diffusion and limited liquid diffusion. Now you will see that over here there is this term dl over V, okay, this dl over V, and over here we have x, which is a unit length. So it means that dl over V must also have unit of length, and whenever you have something like this, you know that it has some significance. So what is the significance of dl over V? So dl over V can be described as characteristics length. What is characteristic length? It says that when you move by this distance at every dl over V distance, the concentration falls, this concentration Cl minus C naught falls by 1 by E. E is the exponent, e to the power 1. So as you move in the liquid by this distance dl over V, the concentration Cl minus C naught falls by a factor 1 over V. So that is the significance of this value dl over V, and as I have already mentioned, its unit would be equal to that of length, because we are dividing x by this quantity dl over v. So now we have covered 3 different conditions for solidification. One was the equilibrium, next was the no solid diffusion but complete homogenization in liquid, and this third one was no solid diffusion and limited liquid diffusion. So now we will move on to even you can say more stringent condition, or again you can say in other words that it is more realistic, and that realistic condition is that we will have some amount of convection in the liquid. So now there is not only diffusion. In diffusion what you are saying is that the liquid is not being stirred or it is not being moved by any other means, and the liquid is standing still. Whatever concentration variation is taking place, it is taking place because of concentration gradient and because of diffusion. But now we will talk about a more realistic condition, which is mixed mode, usually called as mixed mode. What it means is no solid diffusion like always, and there is some amount of convection in liquid. So that is why it is mixed, because it is in between complete homogenization and only liquid diffusion dominated concentration gradient. So there is, you are saying that it is not completely mixed, but it is not even being left alone. So there is no solid diffusion and convection in liquid. And before I move on, there is one thing that I forgot to mention regarding the previous condition. So let me just, that is just one plot that you should be aware of when we are talking about this particular case. So if you look at the overall, we just looked at the concentration changes piecewise, but if you are looking at the concentration as a whole, this is how it will look like. So this was the region that we were calling as steady state. So without spending too much time on this part, which we have already discussed, I will just draw something that you must be aware of. This is initial transient, for which we have given the solution, not derived it. And this is final transient. We have not discussed it, but this is it is not of much consequence, because there is a very small length of this final transient. Okay, so I will leave it at that. I will not get into more. That is all you have to know about that plot. So we will get back to our mixed mode. We are talking about no solid diffusion and convection in liquid. What it does is basically what whenever we say mixed mode, what we are saying is that the distance dl over v that we had over there, that distance is now being limited to another value or a fixed value because of convection to something as delta. So now that there is a small distance delta at which your concentration falls back to the infinity value. So whatever is at x equal to delta, that is the concentration that will remain constant beyond that. So if you were to draw this particular condition, again we are talking, the overall concentration is C naught, remember, and somewhere over here there is a transient, and again we need to talk in terms of the steady state. So over here, let us say we are talking here, this is the concentration Cs, corresponding to this there is a Cl, and because of convection there is only a small distance delta at which it reaches the infinity value. So beyond this So let us call this infinity concentration as C infinity. It may be C naught for some examples, but usually it will be larger than C naught. So this is the concentration in the liquid that will be maintained beyond this point. So now you see, when you are stirring the liquid, there is some kind of mixing, then what you have done is reduced this zone where there was a lot of diffusion and the diffusion layer was falling up, was extending to a very good extent. You have reduced that to a very small distance delta. So that is what you have done, and this is the steady state concentration of solid. So it will remain like this throughout, and this is how the plot for the concentration plot will look like in this condition. So this is what I mean when I say dl over V has been limited to delta. So more appropriate would be that the total diffusion length has been limited to delta, but in effect we can also say that dl over V has been limited to delta, and that is because some convection is present in liquid. So these are two important facts that you need to know. Of course, other than that, you must not forget that there is no solid diffusion, like always. See, the more realistic we are talking about, we have to be strict about the solid diffusion, because solid diffusion is a very, very slow phenomena, and for any casting of significant size, the solid diffusion would be slow, so slow that it cannot homogenize. So no solid diffusion is a much better condition to assume. So these are some of the facts that will be related or that are associated with this particular condition. Now when we are talking about Cs over Cl, this Cs over Cl, if we call, let us call this Cs as a star, because these are the steady state values. So what we will do is represent these by star values, and anyhow all the Cs by Cl is equal to K, which implies Cs star by Cl star is also equal to K. Now when we are talking about the mixed mode, there is another term which becomes very useful, and that is called K effective, and that is given by Cs star by C infinity, meaning what is the partition, or what is the partition of solute in the solid with respect to liquid at infinity. Now in most cases this will become your C naught, but let us not assume that, and let us say this is some concentration at infinity. So this is saying whatever is the solid that is formed, average amount of solid that is being formed, what is its partition with respect to the liquid at infinity, or the overall alloy composition, and this is termed as K effective. Now we will use this to get to, first we will try to get the equation for the concentration change in the liquid part for this, and then we will use it to define or relate K effective with K for this kind of condition, and then we will even extend it to other conditions, as you will see very soon. Again our equation remains same, which is dl del 2 Cl by del x square plus V del Cl over del x equal to 0. So this is our starting equation, and again we said that we are talking about steady state. You remember Cs star and Cl star. So let me write it somewhere, that these two Cs star and Cl star represent steady state values, meaning they are constant. So Cs star and Cl star we are using as values which remain constant. Now with that, let us move on what is the boundary condition that we have over here? We know that at x equal to delta, what should be the value? This is your x equal to 0, remember. So this is x equal to delta. At x equal to delta, what is the concentration of Cl? It is Cl equal to C infinity. At x equal to 0, what is the value of concentration of liquid? It is equal to Cl star equal to Cs star by K. So this is the boundary condition that we have, and if you look at the boundary condition, then Cl as a function of x, using these boundary conditions, again you can find a very straightforward solution for this kind of cases, and it will come out to here you can clearly see that if you put x equal to delta, this will become 0, and then e to the power 0 is equal to 1, therefore Clx is equal to C infinity. So at x equal to delta, meaning at this particular point, the concentration of liquid comes out equal to C infinity, which is what we said. So this equation you must also realize is only valid for a distance between x equal to 0 to delta. You cannot use it beyond x equal to delta, because beyond that the variation is constant. So we are not trying to derive an equation for this. So keep that in mind, that this is valid for x greater than equal to 0 to less than equal to delta, which implies that our equation is in the right form. Next, what we will do is, for the x equal to 0 condition, when we put the x equal to 0 condition, we will be able to put Cl equal to Cl star, and hence we will be able to obtain a relation you would see between K and K effective for this kind of situation. So I will get back to this in the next lecture. Thank you.